Good morning. This is the second day of our conference cycle. Today we're going to have three speakers. First one is André Tomás from Unicamp. Second one is Mateus de Castro Fonseca from CNPEN. And the third one is Carlos Len Cesar from the Federal University of Ceará. Let's go straight to the talks, and I invite André Tomás to present his conference. And I thank him for joining us today. Thank you so much, André.
Okay, thank you. So my screen is online now?
Fine. Showing fine.
Yeah, okay. So thank you guys for inviting me to do this presentation here. So like Professor Hernan said, my name is André Tomás. I'm a professor at the Physics Institute at Unicamp, and I'm from the Biological Physics group, Biological Physics and Cell Signaling group with Professor Aline Mara dos Santos from Biological Institute of Unicamp. So before I start talking about some results we got with super resolution microscopy, I want to talk about how to achieve super resolution for the ones that missed my presentation last week. So let's suppose we have a point in the microscope, and this is your sample, right? This is your sample emitting some fluorescence here, and this sample is about 10 nanometers wide. And after you go to the objective, you get this image. So this point is generate this image in your detector. And this image here, we call the point spread function of the microscope. And this happens because of the diffraction of the light, because light is a wave. When a wave is squeezed through a hole, through some small aperture, it bends or it squeezes the wave, and then the image spreads. So that's how this is happening here, because the light that is being emitted by this particle here is going to an objective, which is basically an aperture. This light is spreading on the detector. And this has a name here. We call it ID disks. And we define the resolution of the microscope, the distance between these two minimum here, which is about 200 nanometers for visible light. And this happens on the XY plane, XXY plane, and XZ plane. And there is a stretch even bigger in the XZ plane. The XZ plane is this plane here when you tilt it and see it by the lateral of the image. And this distance here between these two minima here is about 600 nanometers for visible light. So this is the resolution of this microscope, a point that is smaller than 200 nanometers in the XY plane or 600 nanometers in the XZ plane. It's gonna appear like 200 nanometers in XY plane or 600 nanometer as in the XZ plane. There is another way of defining resolution, which is the minimum distance you can resolve between 2 points or 2 particles. Let's think of this image here as 2 points or 2 particles in your microscope, in your plane of your microscope, and you are seeing it by its side, like here. You just take this XY plane and tilt it, and you see the XZ plane. And the fluorescence emitted by these 2 particles is this graph here. If they are more than 200 nanometers apart, you can resolve them. You can tell it's 2 different particles. If they are close to 200 nanometers, almost below 200 nanometers, you still can tell it's 2 particles apart. So you are at the Rayleigh criterion that we call. And this is the limit, the minimum distance the 2 particles can have to be distinguished. If they are below this minimum distance, they cannot be resolved, and we cannot tell if it's 1 particle or 2 particles together. And this is about 200 nanometers, the distance between these 2 peaks here. So the way of dealing with this, you can manipulate the excitation, or you can manipulate the emission. You can make mathematical approximations or calculations to get rid of the diffraction limit, but or not get rid of the diffraction limit, but to deal with the diffraction limit. You cannot ever get rid of the diffraction limit because light is a wave, and every time a wave goes through a small hole, which is basically the objective, it's going to squeeze the light, and then after the objective, it's going to spread the light. So you cannot avoid that, but you can make some mathematical manipulations or make different illumination patterns, and then you can achieve higher resolutions. So one microscope that do this is the simulated emission, structural illumination microscopy, which is SIM microscopy, and it's based on this phenomena here. So let's suppose we have this sample in your microscope, and you expect to see this image here. You expect to see these circles, these squares, this other square, these simple small circles here. But when you take the image on your detector, after the emitted light goes through an objective, you see this blurred image here. So the effect of diffraction, it's basically blurring your image. You cannot resolve the circles anymore, or the squares here that are sharp here, you cannot see here because it's more or less a circle here. So that's because of diffraction of light. It's blurring your image. But there is a mathematical operation that we can do that is called Fourier transform. And this mathematical operation is just measuring the spatial frequencies you have here. So let's suppose you want to measure how many times these small circles appear in a line or in a column. And then you plot a point in this graph here saying, oh, this circle here appears like 10 times, or let's count 1, 2, 3, 4, 5, 6 times in 6 times 6 rows, right? So you plot a point here, meaning that it's 6 times. So these columns here or these lines here, so each one we can plot a point here and measure the spatial frequency they have on the real image here. But when we do this transformation, this calculation with the real image, we expect to obtain this image here, this Fourier transformed image. But when we go to the objective, the effect of the objective, the diffraction on this Fourier space, the effect of diffraction on the Fourier space image is to clip the image here. And this means that we are clipping the higher frequencies here. Higher frequencies here in Fourier space means small distance here on the real space. This means that if we're clipping the higher frequencies on the real space, we are losing information about the small distance. So this image here, if we take this the Fourier transform, if we take the Fourier transform of this image, it's exactly this image here. If we take the Fourier transform of this image, it's exactly this image here. So the effect of clipping the higher frequencies is to blur our real image. So if we are able to do something with our image and take information from the higher frequencies here, maybe we can get information from the small distance here in the real image. So that's exactly what SIM microscopy does. But how we do it? We do by using an effect that we call Moiré fringes, which is basically interference between two waves. So let's think of these two squares here as two waves, right? Let me come back and pause for a minute here so you can see it. So let's think of these red columns as waves, okay? So we can count the number of red columns and we can get a frequency, right? And the number of green columns, we can count it and then we can get a frequency also. But look at the image and we can see that there is a third frequency here, a white frequency that is not green or red, that is appearing here because of the interference between these two frequencies here, the green and the red. So if we hit play again and change screens, we can see that the frequency of the white wave changed because of the inclination of the green waves on top of the red waves. So this is called Moiré fringes. It's the interference between the two waves. The white waves doesn't really exist, but when you look at the interference between the green and the red, you see the white wave, okay? So let's think that we want to resolve this image here, okay? We cannot, because this is very small and it's below the resolution of my microscope. But let's say that I illuminate this image here with this pattern here. I know the frequency of this pattern. I know the frequency of my illumination. It's the laser of my microscope. And I know the frequency of illumination here. And in my detector, I get this image here, okay? So if in my detector, I get this image here and I illuminate it with this pattern, to be able to get this image here, I must have this spatial distribution on my sample, okay? So I do the Fourier transform or the Fourier calculation in the inverse form and get the information of small distances in my sample. So that's the idea behind structural illumination microscopy. We use a pattern of illumination that interferes with my sample, okay, and generates a third wave. Let's say it's a third wave, and generates a third image, okay, that has interference patterns on this image. And by doing the Fourier transform of this image here, I can do the reverse calculation and obtain the first image with a small distance that I couldn't resolve before. Okay, so that's the idea behind it. So this is the microscope, okay? This is a black box to protect the users from UV illumination and also to make some temperature-controlled environment and atmosphere-controlled environment. And here are all the operational equipment of the microscope. There is a camera here that we do palm and star microscopy, and the scene microscopy is below the table here, okay? So before I go with my results, I want to talk about you. I want to talk to you something that is inherent to microscopy, which is chromatic aberration. Chromatic aberration comes from the fact that the objective is going to focus with each wavelength of light at a different point in the focal plane. So red light, it's going to focus in this point. Oh, let me change here to make it clear. No, it's not pen, it's laser pointer. Okay, so red light is going to focus on this point, green light is going to focus on this point, and blue light is going to focus on this point. Okay, what's the problem with this? If you're doing confocal microscopy with 200 nanometers resolution, that doesn't matter, because when you calculate the difference between green and red or blue and green focus, is going to be below 200 nanometers. It's going to be below your resolution limit, so it doesn't matter. When you do super resolution, you need to take this into account. You need to discount in your image this displacement. Otherwise, if you're measuring distances or measuring correlations or co-localizations, you're going to get false results, because the green and the light, the green and the red light is going to focus on different points, and the distance might be greater or smaller than they really are. Okay, so you need to correct this in your microscope. And a way of correcting this is using, let's say, nano holes, which is small holes we coated on a silver coated cover slip. So we coated a cover slip with silver, metal silver, okay? And on this cover, on this small layer of silver, we made 100 nanometer nano holes that are apart 1.5 micrometers. So if we illuminate these nano holes with white light and detect this white light or this detect this illumination using some filters before my detector, we're going to see that the red light and green light are focusing on different points. So this is coming from the same point, because I'm only changing the detection. It's white light, and I'm only changing the detection. I'm placing a red filter or a green filter in front of my detector, and I'm filtering the light, but it's coming from the same point, but at the detector, they are at different points. So we need to correct this. And one way of correcting this is taking the red image and taking the green image and making a computer program is in telling this computer program that these points are on the same point in the detector, but they are displaced. So we need to calculate the displacement and do a reverse transform from this image to this image and map one image on top of the other image. And then when I take my real image, I do the same calculation and map the green chain on top of the red chain. So we need to do this calculation, otherwise we're gonna get some wrong results. Okay, so that's what I wanted to tell you about super resolution microscopy. And to start to talk about some biological results, here I have a regular resolution image, and here I have a super resolution image. And why I'm showing you this? So if we take a zoom at the nucleus, you can see here that we have three labels. The green one is PTK2, it's a protein. I'm going to talk about it a little bit later in this presentation. Red is gamma H2AX, which is a DNA damage marker, okay? And blue is DAPI, which is DNA, okay? So if we look at the regular resolution, we cannot distinguish nothing, or we can see green and we can see red, but we cannot see the details, okay? We can see that this DNA damage site here has some structure. In fact, or PTK2 is in this position here that is probably interacting with this site. We cannot see this here. So that's why we need super resolution, to be able to see these small features of my sample and understand what is happening with these small features, okay? So going into why we are looking at cardiomyocytes and DNA damage at cardiomyocytes, the reason is here. So if we look at this graph, we see that cardiovascular diseases and cancers are probably responsible for 50% of deaths in Brazil and worldwide. Okay, and cardiovascular diseases are responsible for 30% of deaths. Okay, and 80% of these deaths at cardiovascular disease are heart attack or stroke, and this is due diet, tabagism, or sedentarism. But there is a problem. This becomes much worse when we take into account that patients that had been treated for cancer have 15 times more chance to develop heart diseases, okay, because of the genotoxic stress of the treatment. And this is really, really serious, because you are saving someone from cancer, you are treating that person for cancer, you are curing their cancer, but they are dying from heart disease from heart diseases after the treatment. So we need to understand why myocytes, or why the heart is so susceptible to this treatment, and patients have 15 times more chance to develop some heart disease after chemotherapy treatment. Okay. Our goal here is to understand what is happening after this treatment for cancer. And if we look at the proteins that are related to DNA damage response, we see that PTK2 or FAK, which is the same name for this protein here, which is tyrosine kinase protein 2. If we look at this protein, it's in Portuguese here, sorry for that. If we look at this protein, we see that cells that are knocked out for FAK, there is an increase in cellular death that are knocked out for FAK after DOX treatment. Or myocytes overexpressing FAK develop protection against this treatment. So FAK here, by this work here, we see that FAK is a very good candidate to be responsible, or to not to be responsible, but to have some role in this DNA damage response, okay? And also, if we inhibit FAK in this type of cells here, we see an increase of DNA damage by the increase of gamma H2AX sites. And also, there is a correlation between the high levels of FAC expression and high resistance against chemotherapy and radiotherapy treatment. So FAC here is a good candidate to have some important role in DNA damage response. And we want to understand that because we know that these effects here are mainly for the whole organism, but we want to understand what is happening at the molecular level of these proteins. So our goal here is to understand the role of FAC in the DNA damage response, or the role of FAC in the DNA damage response regulation. Okay, so understand what FAC is doing to help to repair the DNA. So FAC was first found on the focal adhesions. That's why its first name, focal adhesion kinase. But now we saw that FAC can be found at the nucleus also, but its effects on the nucleus is not clear yet. So we are betting that one of FAC effects at the nucleus is to help DNA damage somehow. So here are our first results with FAC and genotoxic stress. And we see that after we treat cells or cardiomyocytes, which are H9C2 cells, we treat these cells with doxorubicin, which is the drug we use to treat cancer, okay? We see there is an increase of FAC at the nucleus. We see this by taking the fluorescence image and measuring the total fluorescence we have at the nucleus here, and we have at the nucleus here for control cells and for treated cells, and we see there is an increase of about 50% of FAC concentration at the nucleus. And this is even more accentuated, this is even higher for phosphorylated FAC. We can see here there is an increase of about almost 3 times of phosphorylation of FAC at the nucleus after treatment with DOX. Okay, so here we see that probably FAC has some hole after you do some DOX treatment with your cells, because FAC is accumulated at the nucleus and it's increasing its phosphorylation at the nucleus also. And here we see the Western blot for total FAC and Western blot for phosphorylated FAC, and we see that expression of FAC and phosphorylation. Let me start again. We see that the expression of FAC does not change from control to DOX, but phosphorylation of FAC also does not change. This means that the expression of FAC is not changing, but FAC is being reallocated to the nucleus. Also, the phosphorylation rate of FAC does not change, but we have much more phosphorylated FAC at the nucleus than we after we treat with DOX than we before control. Okay, so this means that FAC is being recruited to the nucleus to maybe have some effect on DNA damage. Here we have another result, that is genotoxic stress promotes PTK2 recruitment to DNA repair sites. So we label cells with DAPI and PTK2 and gamma H2AX labels to see if this accumulation has something to do with DNA damage sites. And here we have a 3D plane or several 3D or several planes along Z direction for control and for 2 doxo treated cells. And we can see that after the doxo treatment, first, before doxo treatment, we don't see any DNA damage at control cells, but after doxo treatment, we see DNA damage sites. And here, in these 2 figures here, we see that FAC is colocalizing with DNA damage sites. This means that the recruitment of FAC to the nucleus might have something to do with DNA damage. Okay, so the cell has many DNA damage sites, and FAC is being recruited to the nucleus, and this recruitment is ending at some points. Not all FAC is correlated to DNA damage sites, but some of FAC is correlated, is localized, not correlated. It's a better expression. is localized at DNA damage sites. We can see here, one here and one here. Also, the phosphorylation of FAC, of phosphorylated FAC, is localized with DNA damage sites. And this is the same idea before. This is control, this is doxo-treated cells, and green is for phosphorylated FAC, and red is DNA damage sites, okay? And when we see the doxo-treated cells, we see that phosphorylated FAC is correlating, or not correlating, it's localized at DNA damage sites. And even more, we are seeing that these DNA damage sites have some structure around normal DNA. So the conclusion here is PTK2 is recruited to DNA repair sites. PTK2 catalytic activity might be important to this DNA reparation. And also, PTK2 interacts with the DNA hexagonal structures, like we can see here, okay? So after that, after we saw that FAC is recruited to DNA damage sites, and phosphorylation of FAC might be important to this repair, or to help this repair, we started to look at the interaction of PTK2 with some proteins that are related to DNA damage, that protein that is known to be related to DNA damage repair. Okay, so we started looking at the interaction of PTK2 with BCLAF1, which is a protein from the BCL2 family. It's mainly nuclear localization, okay? It acts on many biological processes. Excuse me. Okay, it acts on many biological processes. It's related to cell survival and death regulation. And the main reason we start to look at PTK2 interaction with BCAF1 is because of the DNA damage repair function of this protein here, and it's also because it's related to mRNA splicing of repair proteins. Okay, BCLAF1 is related. No, it's not related. It's responsible to do splicing of mRNAs of repair protein. So we wanted to see if PTK2 interacts with this protein. Okay, so the answer is yes. We see at the immunoprecipitation here that after doxo treatment, sorry guys, I have to let me. Okay. We see at this immunoprecipitation here that after doxo treatment, we see an increase of interaction between FAC and BCLF1. Okay, so here we have control cells, and here we have doxo treated cells, and we can see that BCLF1 and FAC are presented, or we can find FAC and BCLF1 on control cells. But after doxo treatment, we see that BCLF1 and FAC migrates to some clusters here. Okay, we can see very clear here that these clusters are very bright, and here in the PTK2 images, they are not so bright, but we still can see them. And if we get a zoom of the regions, okay, so this is control, we see some interaction, but after treatment of doxo, we see much more interaction between doxo and FAC and BCLF1. Between FAC and BCLAF1, okay? And if we calculate the interaction between them by the correlation between FAC and BCLF1 in these regions here, we see there is an increased interaction between them. So the way we do this is we take a cluster of BCLF1, calculate its area, and then double this area here by a circle. Okay, and then we take this circle and calculate the correlation between green channel and red channel. Okay, and here on the first line is the clusters, and here on the second line it's the random positions at the nucleus. Okay, it's regions that there are no clusters of BCLF1 or no clusters of FAC. Okay, and when you do the calculation of the correlation position between these two, Sorry, guys. I'm getting called by my supper here. Let's see. I'll call them after I finish this. Okay, so if we compare the loci that we're calling, or the clusters of BCLF1 and FAC, and we compare the random regions, we see that there is a correlation, a position correlation of the loci of about 0.8, okay? And we have a correlation position of 0.4 between in the random position. So this means that whenever we have a cluster of BCAF1, we have a cluster of FAC also, okay? And after extensive DNA damage, there's an increase of TK2 and BCAF1 clusters. If we treat cells, okay, now it's new. If we treat cells with dox for 3 hours and do the measurements, if we treat cells with dox for 3 hours and let the cells recuperate for 24 hours, and if we treat the cells for 3 hours with dox and let them recuperate for 48 hours, we see that there's an increase of gamma H2AX sites, meaning that cells are not being able to recuperate this treatment, okay? And here we see that this no treatment, this is control, this is 24 hours of treatment with doxo, and this is 48 hours of treatment with doxo. And the number of clusters is higher on 24 hours treatment. So this means probably that with this 24 hours treatment, the cells are still trying to recuperate, but at this 48 hours of treatment, the decrease of clusters might show that the cells is recuperated, but this is not true, because if we see these cells at 48 hours treatment, we see that they are dying. Okay, so the number of clusters are smaller, but the cells are dying. So these clusters are somehow related to apoptosis of cell. Okay, so the question here is how these clusters are related with cell apoptosis. And the answer is here, because if we do an experiment labeling these 3 proteins, so here we are labeling PTK2, okay, we are labeling BCLAF1, we are labeling gamma H2AX, okay, so here in red and green is PTK2 and BCLAF1, and in magenta is gamma H2X, the DNA damage sites. And we see here that these clusters are near DNA damage sites. Not all DNA damage sites have clusters, but almost all clusters of PTK2 and BCLF1 are near some DNA damage sites. And we can do a calculation of this. We can do a calculation and measure the probability of having these clusters near a DNA damage site. And we see that the probability is very high, because the correlation coefficients of having these clusters near DNA damage sites is above 0.5, which means that almost every cluster is near a DNA damage site. And if we calculate the position correlation of these 3 proteins, we see that the clusters are on top of each other. We see that clusters of FAC and BCLF1 are on top of each other, because we see almost a correlation of 1 here. And we still see a correlation between BCLF1 and gamma and FAC, because they are near to each other, but they are not on top of each other. So the question here is, what is this cluster doing with that is preventing the cell to be able to recuperate of DNA damage? So our hypothesis here is that these clusters somehow are preventing FAC of interacting or doing its job inside the nucleus, because we know that FAC interacts with p53, which is a transcription factor that helps transcription factor. Oh, it's very hard to say in English this, but it's a transcription factor that regulates cell viability, okay? So FAC degrades p53 and helps cell viability. But if we stop FAC from interact with p53, we might not degrade p53, and then cells goes to p53 increases cell mortality, okay? So that's what we think is happening here, and we could only see that because we were able to do super resolution microscopy and see these clusters here, and we saw that these clusters are near DNA damage sites, and we saw that these clusters or cells presenting these clusters are almost dead already. So that's why our hypothesis is in this direction, that BCLAF1 is, we don't know it yet, we bet that is kidnapping FAC and stopping FAC from interaction with some other proteins, especially with p53, and then cells are going to apoptosis. So that's what we think is happening here. So that's what I had to talk about seeing microscopy. Now I'm going to talk about storm and palm microscopy, and I don't have any really good results to show you now, but I'm going to show you some technical aspects we have to take into account to do a good storm or palm microscopy. So just to remember how we do palm microscopy. So remember that we had these two particles here that we couldn't resolve. Okay, and but let's think that we can find a way to make this fluorescence go away. Okay, so which is this, and then we light one cell, one particle, and we take its fluorescence, we light another particle, and we take its fluorescence, and then we can resolve these two particles apart. And why we can do that? Because if we look at this image here, which is basically this image here, but in 3D, we see that we have a much higher resolution here at the center than we have at the true minimum here of the iris disk. So if I take the image of just one emitting particle, and we take this fluorescence and we fit this fluorescence to a mathematical function and find its center, we have much higher precision than we have here at the width of this function. So this is basically what we do in palm or storm microscopy. So here it's the resolution gain we have in storm and palm microscopy. The difference between these two, they are the same type of microscopy, but palm is done with photoswitchable fluorescence proteins, and storm is done with organic dyes. That's the only difference. Okay, so here I have a movie of me doing palm microscopy in neural cells. So this is dendrites of a neuron. Okay, and the bright spots here are a protein of postsynaptic protein, HOMER1. Okay, and it is transfected with a photofluorescent protein, and each time I'm shooting a pulse of UV light, you see the fluorescence. Okay, and I'm acquiring the fluorescence and doing the calculation of its center to find the position of each molecule. So you're seeing here that a good image needs about 1,000 frames, 2,000 frames, 3,000 frames. It depends on what resolution you want to achieve. Okay, and here it's a storm image. So this I have the illumination laser here. This is the fluorescence, and then I shot a very bright pulse of UV light, and you're seeing the blinking of the molecules, and I'm detecting each molecule and do the calculation to find its center and get the resolution we want. Yeah. Why I'm showing you this? I'm showing you this because you're seeing that it takes a very, very long time to be able to get a good image. And there's a consequence of this. The consequence is drift, okay? There is a drift in the sample that is, the sample is moving when you are acquiring your image. So here it's an incorrect image and here it's a corrected image. So you can see these fibers here are stretched in this direction because the sample moved along the experiment. And we need to do so, and we need to do something to be able to correct this, okay? So one way of doing it is to track a fixed particle in your sample, a bead, a polystyrene bead, or a glass bead, or something that is fixed. You know that is not moving during your acquisition, and you do the calibration, and you do the calculation here, and you do the calibration, and then you are able to correct the drift in your image. So you're seeing here a particle, and it is moving. I don't know if you can see that because of the resolution of your video there, but let me, oh, okay, I could see here. Like here. So if I click play, so you can see it's moving, okay? And we need to correct that. Otherwise, some features in our image is gonna be stretched. Okay, there's another way of doing it, which is using the Fourier transform of the image. So you take your image at 0 minutes or 0 seconds of acquisition, and then you take the Fourier transform. So there's a bright spot, and you make sure this bright spot comes back to the center every time you take the Fourier transform of your image, and then you correct the sample drift also. Okay, and that's it. I had to talk to you today, and I can answer any question you might have. Thank you for your attention.
Thank you, Andrea. Thank you so much for this comprehensive view of super resolution. And let's see if there is any question in the Facebook. I have a question for you because I thought colocalization in physics was impossible. And in my opinion, as you increase the resolution, colocalization disappears. At the end, there is no colocalization at all.
Yeah, you're right. This is not true colocalization. It's not a molecule colocalization, okay? But you can define some region of colocalization. Let's say in a region of 20 nanometers, I have my 2 particles, so they are colocalized. So you can define types of colocalization, and with these types of colocalization, your degrees of colocalization, you can do the calculation and say, wow, with this degree of colocalization, they are colocalized. That's one way of doing it. You're muted.
Yeah, we don't have any questions so far. And I will thank you again for joining us today. And if the attendees want to ask questions, I will ask them to send them the questions to us or straight for you. And I'm sure you're going to be happy to answer any question they might have.
Yeah, sure, no problem.
So we're going to have a small intermission here, a break, and we'll be back by 11 o'clock with Matheus Fonseca talk. Thank you so much, Andrea. You are invited to stay with us.
All right, thank you. Thank you for having me.
Okay, thank you.